Bom, boa tarde a todos e todas. Bem-vindos ao seminário do DRCC dessa semana. Essa semana a gente tem o prazer de receber o Mauricio Ferreira. Então, o Maurício fez seu doutorado aqui no IFGW, com a professora Cristina, e ele trabalhou no tema de funções de Green não perturbativas da QCD. Após o seu doutorado, ele realizou um pós-doutorado aqui também no IFGW, mas com o professor Jun Takahashi, estudando efeitos da fase pré-hidrodinâmica em observáveis de colisões de íons pesados relativísticos, mas ao mesmo tempo ele também continua atuando na área de funções de Green não perturbativas da QCD, e agora ele está de partida para a Espanha, para a Universidade de Valência, onde ele vai realizar mais um pós-doutorado sob a supervisão do Ioannis Papavassilio, estudando mecanismos de geração dinâmica de massas na QCD. Então, muito obrigado, Maurício, por estar aqui conosco e pode começar.
Tá bom. Bom, gente, na verdade, eu preparei a apresentação em inglês, eu vou, a não ser que alguém tenha alguma objeção, vou apresentar em inglês, ok? Deixa eu só dizer que, caso vocês tenham qualquer pergunta, podem interromper, não sei que vocês prefiram deixar para o final. E, antes de eu começar, de fato, só queria agradecer, então, a oportunidade de apresentar esse seminário, e, em particular, agradecer ao Adriano e o Guilhermo pelo convite. So, today I'm going to present some of the results that we have gotten recently about the dynamical mass generation, specifically of gluons in QCD, although I will also talk shortly about dynamical mass generation of quarks. So this is a very important topic, as you shall see, because QCD really, as a theory of the strong interaction, it hinges on the phenomenon of dynamical mass generation. So a lot of this work has been done there in the Institute of Physics at Unicamp, in collaboration with Professor Cristina, and has been developed during my master's and PhD, mostly, and more recently also partly in my postdoc. So, QCD is a theory, the quantum field theory of the strong interaction. It is described by this well-known Lagrangian, which is composed of three fundamental fields: the quarks, which are the fermions of the theory, the gluons, which are the gauge bosons of the theory, and the ghosts, which are not real particles in the sense that they are not observable in the spectrum of the theory, but they are necessary to fix the gauge and quantize the theory consistently. Now, QCD and these three fields with this one-line Lagrangian, which looks very simple, actually encodes a plethora of phenomena. In particular, confinement, which is the fact that we do not see the quarks and the gluons individually. We don't see them as free particles, only as bound states. We have a rich spectrum of such bound states, which are called the hadrons. And another very important property of QCD, which will be the focus of this talk, is the dynamical mass generation. That is, QCD somehow generates masses that are not present in this simple Lagrangian. And in large part, this phenomena that QCD encodes happen because of this property of QCD, which is that it is a non-abelian gauge theory, which implies that it has self-interaction. In particular, the gluon, right, it interacts with itself. So in addition to the interaction of the gluon with the quarks, we have also interaction of the gluon with itself through these two vertices, which appear here in this diagrammatic representation of the Lagrangian, the 3-gluon vertex and the 4-gluon vertex. Now, the simplicity of this Lagrangian is actually deceptive. And this is because QCD is really not simple at all, especially not as far as it regards those three phenomena that I mentioned before: confinement, the hadron spectrum, and dynamical mass generation. So QCD, we know, is an asymptotically free theory. This has been shown by Politzer, Gross, and Wilczek. And what this means is that at large momenta, the coupling constant of the theory is small. Okay, the running coupling of the theory is small, as you can see in this figure of the running coupling from the particle data group. And that in turn implies that in this regime, at very large energies, we can use perturbation theory reliably to compute QCD quantities. But in the infrared, the running coupling becomes large, and the perturbative expansion breaks down. It can no longer be used reliably. Now, it is precisely in the infrared, in this region of 1 GeV and below, that these three phenomena that I mentioned take place. Okay, both the confinements and the hadron spectrum, the rich hadron spectrum of QCD, and the important phenomenon of dynamical mass generation. So in order to study this phenomena, we need non-perturbative tools to study QCD. Now, in particular, I will be focused on the phenomenon of dynamical mass generation, which means that QCD generates masses that are not present in its Lagrangian. So let us understand what this means in more detail. So if we recall the Lagrangian of QCD, we will see that the gluons at the level of the Lagrangian are massless, and this is required by the gauge symmetry of the theory, right? We know that you cannot add a mass term to a Lagrangian of gauge boson because if you do, it will break the gauge symmetry. And the quarks, they do have masses, okay, which are generated by the Higgs mechanism, basically. But the masses of the quarks are tiny in comparison to the masses of the hadrons that they constitute. So in particular, the mass of the up quark is of 2 MeV, and the mass of the down quark is of 5 MeV, and yet the masses of the proton and the neutron are almost 1,000 times bigger. So they are on the order of 1 GeV. So perturbatively, if you start with massless particles, you cannot generate masses for them, for the gluons and the quarks. And yet, the universe is full of masses that are related to the strong interaction, the masses of the proton, the neutron, the pion, and so on. So somehow QCD generates these masses through its dynamics. Okay, this is not directly, it's not explicit in the Lagrangian of QCD. And it is this dynamical mass that QCD generates that amounts to about 98% of the mass of the visible universe. I mean, the masses excluding dark matter, right? Now, when I say that QCD somehow generates masses dynamically, it is important to know that this is not something completely new to QCD. There is precedent for this. Okay, so this is not something completely crazy. Indeed, there is a long history in quantum field theory of theories that generate masses dynamically. Okay, the fields can acquire masses that are not present explicitly at the level of the Lagrangian of a particular theory. It all started with superconductivity, okay, a theory in condensed matter, where we know that the photon becomes massive, okay, inside the superconductor, and that is what explains, for example, the Meissner effect. Now, this has inspired many developments in dynamical mass generation in other models, okay, including relativistic models. So, for example, the Nambu-Yonah-Lassinier model, which was the first model wherein fermions that are massless at the level of the Lagrangian become massive through the interaction. And of course, we have the Higgs mechanism, which generates the masses of the Z and W bosons in the standard model of particle physics. So somehow, phenomena like this have to happen in QCD also, in order to explain the large masses of the hadrons, okay, the masses that are much, much larger than the tiny masses of the quarks that are present in the QCD Lagrangian. But what exactly becomes massive in QCD? Is it the quarks or the gluons? The answer is that probably both. Okay, both the quarks and the gluons have been proposed historically to acquire dynamical masses in QCD. So the quarks, the dynamical generation of quark masses is associated with the phenomenon of dynamical chiral symmetry breaking. Okay, which means that at the level of the Lagrangian, if you disregard the masses of the quarks, you have symmetry under chiral transformation of the quark fields, but then QCD somehow breaks that symmetry and generates quark masses. But also, it has been proposed that gluons can also acquire masses dynamically, and this is attached to a different mechanism that I will explain later on, which is the Schwinger mechanism. Now, to study this phenomena, many frameworks attempt to understand the Green's functions of QCD, that is, the propagators and vertices of the theory. Now, how can we compute these Green's functions in the first place so that we can study them? Well, of course, in the ultraviolet regime, where perturbation theory holds, you can compute them within perturbation theory. But since we are interested in phenomena such as dynamical mass generation, we cannot rely on that. We need non-perturbative methods that can access the QCD Green's functions. Now, why study the QCD Green's functions? You may say, for example, that the Green's functions are gauge and renormalization points dependent, so they are not really observables, right? Nevertheless, they can be combined to compute observables. And more importantly for us, for the contents of this talk, the Green's functions encode information about generation of masses, right? So the non-perturbative infrared behavior of the Green's functions of QCD changes qualitatively when you have dynamical mass generation taking place. So just to give you a very simple example, let us consider the propagator of a scalar particle, for example. So it is something of this form, 1 over q squared minus the mass squared. Now, if you start with a mass, with a massless propagator, you have 1 over q squared. So if you plot it, it diverges at the origin. But then if somehow you do a numerical calculation, for example, from some other method that has access to the non-perturbative behavior of the Green's functions, and you find that the propagator saturates at the origin, this means that you have somehow generated a mass for that propagator. It is no longer that 1 over q squared. Now, what methods are there for us to study the Green's functions of QCD non-perturbatively? So one method is the lattice QCD. Essentially, lattice QCD is a Monte Carlo approach to simulate the gauge field itself, the gluon, and also the quarks, but in a discrete Euclidean spacetime. This method has been constructed by Wilson, and it was originally meant to compute gauge invariant quantities. But it can also be used to compute Green's functions after an appropriate gauge fixing. The power of this method is that it has controlled error parameters, right? So when we do the simulations using Monte Carlo lattice QCD, we have, for example, the spacing of the lattice, the distance between 2 points in this lattice. And we know that in the limits when this spacing goes to 0, we recover the original continuum theory. So we have a parameter here, the lattice spacing, that controls our error. However, QCD is not almighty by any means. It has several limitations. One of them is that they are extremely computationally intensive. Many QCD simulations really are done in supercomputer. But even more important than that, there are certain things that QCD just cannot compute. In particular, and this will be important later on, QCD can only compute, lattice QCD can only compute transverse projections of the Green's functions. It cannot compute longitudinal components if they have any, right? So if you have a Green's function that has Lorentz indices, QCD on the lattice can only compute the transverse parts of these Green's functions. Another method is based on the Schwinger-Dyson equations. These are the equations of motion of the Green's function. So they are like the Euler-Lagrange equations for the quantum theory. And they form a tower of infinitely many coupled nonlinear integral equations. So to give you an example and also set up the notation that I will be using throughout, I bring here a diagrammatic representation of the Schwinger-Dyson equations of scalar phi to the fourth theory. So in this diagrammatic representation, the circles, they represent fully dressed propagators and vertices. Okay, so these are not your textbook propagator, the tree-level propagator. This is the full propagator, the quantity you're trying to solve for, the unknown of your equation. So this first equation here, for example, it relates, it is an equation for the scalar propagator, but you note that it also involves the full 4-point vertex of the scalar theory. This quantity, in turn, satisfies another equation, which relates it to a 6-point function, and so on and so forth. So you have, in the end of the day, an infinite system of equations. Now, in principle, the Schwinger-Dyson equations can compute any Green's functions and in full detail. They do not have, for example, the limitation of the lattice that the lattice can only compute transverse tensor structures. The Schwinger-Dyson equations can compute the full tensor structure of a given Green's function if it has tensor structures. So in principle, Schwinger-Dyson equations can compute anything. In practice, it's really not simple. And this is because it is an infinite system of equations. To solve them, usually what you have to do is to truncate this equation by neglecting some diagrams. So for example, you could come here and neglect this 6-point function that appears in this Schwinger-Dyson equation so that you have a closed system of equations. And then you try to solve this numerically, because even after truncation, you cannot generally solve them analytically. Now, the problem of this is that this truncation, it is hard to control the error that it introduces. And moreover, it's not just a quantitative matter. Okay? It's not simply a matter of maybe your error is 5%, maybe it's 10%. Sometimes by truncating the equation, you break the symmetries of the theory. So you have to be really, really careful in constructing a truncation in such a way as to preserve the physics that you are trying to understand. Now, using these tools, lattice simulations and Schwinger-Dyson equations, we can compute Green's functions, and with this, we can assess the phenomenon of dynamical mass generation in QCD. So to begin, I will talk first about the best understood phenomenon, the best understood of this mass generation mechanisms, which is the quark mass generation. So very generally, the quark propagator, it can be written in this form. Z is the quark wave function. P slash is the momentum of the quark contracted with the gamma matrices. And M is the so-called quark mass function. Okay, so this is a completely general expression. Now, if you start with a Lagrangian that has 0 quark masses, and you do perturbation theory, you will find that this function m will always be 0, order by order in the perturbative expansion. However, this is not so non-perturbative. It turns out that the Schwinger-Dyson equation for the quark propagator, it has a phenomenon that is called bifurcation. It has essentially 2 kinds of solutions depending on the strength of the kernel of the equation, basically the strength of the interaction between the quarks and the gluons, okay, which is highlighted here by this purple box. So specifically, if the interaction is weak, the solution of this Schwinger-Dyson equation will always have m equals to 0. But if the interaction is strong enough, the nature of the solution changes qualitatively, and you start to have non-zero mass. So this is bifurcation. And it turns out that the state-of-the-art results from both Schwinger-Dyson and lattice simulations show that indeed we are in the regime for QCD to generate quark masses. In other words, the interaction between the gluons and the quarks that is encoded by this vertex here is strong enough to generate quark masses. Okay, in other words, to yield a solution a non-zero quark mass function. So here on the left-hand side, I'm showing Schwinger-Dyson results from a work of mine with Christina. And you see here that it has a very different behavior than the perturbative expansion would give. In perturbation theory, if you start out from massless Lagrangian, you will always have massless quarks. But what we find from Schwinger-Dyson equations is that, like I said, it is non-zero because the theory is sufficiently strong. However, this mass, it does recover perturbation theory in a very particular sense, namely that even though in the infrared we have a non-zero quark function, quark mass function, this function decreases very quickly as we increase the momentum of the quark. So in the ultraviolet, that is for large momenta, we do end up recovering perturbation theory. All right, so when I say that the Schwinger-Dyson equations generate masses for the quarks and that this is different from perturbation theory, I don't mean that the Schwinger-Dyson equation somehow invalidates perturbation theory. I simply mean that the Schwinger-Dyson equations hold in a regime where perturbation theory does not. Now, these are Schwinger-Dyson results, and of course, like I said, Schwinger-Dyson equations have difficult to control truncation errors, but this result is also being confirmed by lattice simulations. Okay, so this is one of the most recent lattice results that I'm showing on the right-hand side. And the lattice can also simulate this quark mass function, and you can see that it behaves exactly the same as the Schwinger-Dyson prediction. Okay, so it's non-zero at small momenta, but it drops quickly to 0 in the ultraviolet recovering perturbation. So with this, what I want to do here is to illustrate the synergy, really, between Schwinger-Dyson and lattice results. Both of these methods, they have their limitations, but when combined, one verifies and explains the other, right? One gives credibility to the results that are found by the other. Now, quark mass generation is a phenomenon that is fairly well understood. I don't think there is anybody today that doubts that this phenomenon happens in QCD. And we understand why. Like I said, we have this bifurcation phenomenon in the Schwinger-Dyson equation of the quark propagator. Now let's talk about gluons. For gluons, the situation is more complicated. The mechanism by which you could somehow generate a gluon mass is more delicate. So the first to propose that gluons may also acquire masses in QCD was Mike Cornwall in the early 80s. But it was only very recently, in the late 2000s, that lattice simulations achieved the point where we can compute the gluon propagator in sufficiently large volumes of lattices in small spaces where we can trust that the infrared behavior is stable. And when we did that, what people started finding is that the gluon propagator, it saturates. Now, if you remember from a few slides before, the saturation of a propagator means that a mass has been generated, okay? In perturbation theory, if you were to compute the same quantity, what you would find is that it blows up at the origin. So this now is something that is that has been found in several lattice simulations. All of the state-of-the-art simulations done on the lattice have been finding the same feature, and it is an unequivocal sign that the gluon acquires a mass in the infrared in QCD. Now, the situation here is a bit different from the quark, because we have all been told that you cannot have a mass for a gauge boson, right? In particular, you know that you cannot add a mass term to the Lagrangian of a gauge theory for the gauge boson. But this is not really the whole story. While you cannot put a mass in the Lagrangian for the gauge boson, you can actually generate a mass dynamically for it. And this can be done without violating any of the symmetries of the theory. So this is the point that has to be emphasized. So what I'm going to show you in the next slides is how we can explain this phenomenon here, how QCD generates a mass for the gluon without violating the gauge symmetry. So the person who realized that this can happen for a gauge theory in general, not for QCD in particular, was Schwinger. Okay, so Schwinger, he has shown that a gauge boson can acquire a mass, even if the gauge symmetry forbids a mass term to be explicitly put in the Lagrangian for that gauge boson, provided that the vacuum polarization function has a pole at zero momentum. Let me explain what this means. So these diagrams here are a representation of the photon propagator in QED. Now, it can be shown from completely general premises that the gluon propagator can be written in this form. It is Q squared, the inverse of the gluon propagator. It is equal to Q squared times the tree level, which for this quantity is 1, plus a function here, a scalar function, which is called the vacuum polarization. Now, if you look at this equation, and you assume that this vacuum polarization is finite when Q equals to 0, or even if it diverges, but it diverges weakly, say like a logarithm, then it's clear that the inverse propagator, it goes to 0 at the origin. And if the inverse propagator goes to 0, that means the propagator diverges, right? So it is massless. Now, if for some reason the vacuum polarization has a pole at the origin, so it has a strong divergence of the form C over Q squared for some constant C, then the inverse propagator will saturate, obviously, at the origin, and this can then be understood as the mass, right? So the propagator will saturate at the origin. Now, you see that there is kind of a connection to the mechanism that we had there in for quark mass generation, but it's more delicate. There, in the quark mass generation, it sufficed that the interaction was stronger than a certain finite amount to generate a mass. Here, for the gauge bosons, it is more complicated. It's not enough to have a finite. There is no finite value of the vacuum polarization that will give a mass to the gauge boson. You have it. You need this to be infinite, really, and not even just infinite, because just a logarithm won't do. You need this to be a pole. So how can the vacuum polarization acquire such a pole in the first place? Is that even possible? Well, Schwinger has shown that yes, that this is possible, and he even constructed an explicit example, namely QED in one space dimension. In this case, the theory is actually solvable analytically. It can be solved exactly, and it can be shown that indeed the vacuum polarization of the photon in 1+1 dimensions, it has a pole, and this gives the photon a mass, which is the electric charge divided by square root of pi. Now, that is a model that has been constructed to be simple, constructed to be solvable, and the mechanism by which the vacuum polarization acquires a pole is not really relevant directly to QCD. It's not the same thing. Just to clarify, what happens in QED is a pole in the interaction between the electron and the photon. But in QCD, it turns out that what gives the vacuum polarization a pole is the gluon self-interaction. It doesn't seem to have anything to do with quarks, with fermions. So how can the vacuum polarization of the gluon acquire such a pole? What triggers the Schwinger mechanism for QCD? Well, the idea is the following. Because the gluon is self-interacting, you can imagine that if the interaction is sufficiently strong, between all of the ways that the gluon can interact with itself, it can form a bound state, right, of gluons, just as you can form bound states of quarks that are the hadrons. Now, moreover, if this interaction is very, very strong, really, then this bound state can actually be massless, okay? And this endows the vertices of the theory with poles at the origin. So just to consider one example, if you look at the 3-gluon vertex, that is the function that encodes all of the ways that 3 gluons can interact, then in particular, what can happen is this. A gluon opens up into 2 gluons, then they bind into a massless bound state, and then opens up again into 2 other gluons. But because the propagator of this bound state is massless, it is of this form, 1/q². So that the contribution of this transition here from one gluon to a bound state and then to 2 other gluons will be a pole in the 3-gluon vertex. Now, whenever I say that the Schwinger mechanism is activated in QCD by the formation of massless bound state poles of gluons, some people might be triggered to think that this has anything to do with glue balls. So I have to warn you before I go on that these bound states that trigger the Schwinger mechanism are not glue balls, not at all. So they are different from glue balls in many ways. First of all, glue balls are color singlets. On the other hand, if you look at the quantum numbers of these bound states that are necessary to trigger the Schwinger mechanism, you can show that this is actually a colored bound state. Okay, it's not a color singlet. The second difference I have actually already said, which is that the Schwinger appear in the spectrum of QCD. That is, glue balls are in principle observable. We have not yet found glue balls experimentally because there are several difficulties in doing so, but it is a consistent prediction of QCD that there should be these glue ball states as observables. On the other hand, the bound states that trigger the Schwinger mechanism, they do not appear in the spectrum. The situation here is somewhat analogous to what happens in the Higgs mechanism. There in the Higgs mechanism, if you recall, when you break the gauge symmetry in the Higgs mechanism, there are the would-be Goldstone bosons, okay, that are massless states. However, these would-be Goldstone bosons, they are, in the terminology of the Higgs mechanism, said to be eaten to generate the mass of the gauge boson, right? So the situation here is very similar. These bound states do not appear in the spectrum of QCD, and that is very important because we don't see any such particles, right, experimentally. And they don't appear in the spectrum because they are eaten to generate the gluon mass. And finally, there is one more property of these bound states that I want to emphasize, which is that when they couple to the 3-gluon vertex, they can only do so by means of the longitudinal tensor structures of the vertex. This will be important later on when we approach the problem of trying to test whether this really happens in QCD. Now, back to the Schwinger mechanism. If you have poles in the vertices of the theory, and in particular in the 3-gluon vertex, it turns out that these poles will appear also in the vacuum polarization of the gluon. So in particular, the gluon propagator, it satisfies the Schwinger-Dyson equation that, like the one that I have shown you before for QED, has the tree level, Q squared, plus radiative corrections, which are encoded by these diagrams. And if you have a pole here in the 3-gluon vertex when Q goes to 0, this will give a pole to the vacuum polarization of the gluon, which will, by the Schwinger mechanism, yield a mass for the gluon propagator. So this would be the qualitative explanation of this observation that the lattice has, that the gluon propagator saturates at the origin. Now the question is this really what is happening? Or is this something else? Is this saturation point some artifact of the lattice? Or is this that it does have a mass, but it is generated by some other mechanism? So what we want to do next is to try to test whether this mechanism really occurs in QCD. So to begin, the presence of these bound states that trigger the Schwinger mechanism in QCD is not something that is put in by hand. As I emphasized before, we are not changing the Lagrangian of QCD, okay, at all. We're not adding any new fields. We're not adding any new terms to the Lagrangian. So somehow, the formation of these bound states is encoded in the QCD dynamics, and then we should be able to calculate. We should be able to see, just like we did for the quark mass generation, whether the vertices and the propagators of the theory have the right properties to form these bound states. Now, bound state formation in quantum field theory, it can be described by the so-called Bethe-Salpeter equations. They are cousins of the Schwinger-Dyson equations. Okay, they are also coupled nonlinear. Sorry, in this case they are actually linear, but they are coupled integral equations and an infinite amount of integral equations. But they are specialized to the limit where the bound state acquires a pole. Now, the poles that trigger the Schwinger mechanism are no different. They also satisfy Bethe-Salpeter equations, and we can use those to try to determine whether QCD has the right properties to form, to trigger the mechanism. So in particular, if the 3-gluon vertex has a bound state transition, then it can be shown that it can be written in this form. The full vertex is a pole-free part of the vertex plus something that has the pole, and the residue of this pole satisfies this a Bethe-Salpeter equation, which is represented diagrammatically here. So because of this equation, because this residue satisfies the Bethe-Salpeter equation, it is called the Bethe-Salpeter amplitude. And now we can use this equation to try to see if this equation has non-zero solutions. You see, this equation is homogeneous. So in particular, C equals 0, that is, no pole, is always a solution. Okay, so the absence of a bound state is a solution of theory. What we have to see is that whether C different from 0 is also a solution. That would be the statement that QCD has the right properties to form that massless bound state. Now, in this equation appear ingredients that we can compute, again, either from lattice or from Schwinger-Dyson equations, such as the gluon propagator that I have already shown. And we can put into this equation the ingredients that we have calculated and solve it, even if only numerically. And indeed, when we put here the state-of-the-art ingredients that we have for the quantities that appear in this Bethe-Salpeter equation, we do find non-trivial solutions for the amplitude C. Okay, so this in particular is shown here on the right is indeed a numerical solution with realistic ingredients obtained from state-of-the-art studies of QCD. So this is the first encouraging evidence that the Schwinger mechanism can indeed the Schwinger mechanism can happen indeed in QCD. But now, like I said, Schwinger-Dyson equations in general have truncation errors, and so do the Bethe-Salpeter equations. Okay, the Bethe-Salpeter equations also have a truncation. So for example, here, there should actually be other diagrams that I'm not showing because we cannot handle the full complexity of an infinite system of equations. So you may say maybe this non-trivial solution that we have is completely artificial. This is just a result of our truncations. So we want to do better than just say, well, under certain truncations, we have a non-trivial solution. We want to be able to analyze lattice data and see if there is evidence of the formation of these poles directly. So next, you could ask, well, lattice simulations can compute Green's functions. Now, the three-gluon vertex is a Green's function. So can we just simulate the three-gluon vertex on the lattice and see if it has the necessary pole to trigger the Schwinger mechanism? Unfortunately, no. And the reason for this is because, like I said, when I introduced lattice simulations, there are certain things that lattice cannot compute. Even when it can compute certain Green's functions, it cannot compute them fully, not all of their tensor structures. And in particular, the poles that are associated to the Schwinger mechanism in QCD, they are coupled longitudinally. They belong to longitudinal tensor structures of the vertices, but the lattice, like I said, can only compute the transverse tensor structures of the vertices. So if we split the vertex, like I did before, into a pole-free and a pole part that is longitudinally coupled, the only part that the lattice can compute is this one here highlighted in green, only the pole-free part. So unfortunately, we cannot just compute this directly on the lattice and see whether the Schwinger mechanism happens or not. So in the past, we have explored some possible indirect signals. And to this end, what we have done is to compute other Green's functions of QCD and see if there is any one of them that would show a sign of the Schwinger mechanism. For quite a while, we did not find anything very strong. We had some very indirect signals only. So for example, the ghost propagator can also be computed on the lattice, and we can show that the Schwinger mechanism has some implications for it. So in particular, the Schwinger mechanism leaves the ghost massless, right? So it generates a mass for the gluons, but the ghost, on the other hand, remains massless the ghost propagator, it can be shown to be of this form, 1 over q squared, essentially near the origin. And lattice simulations confirm this. So this qualitative prediction is in good agreement with the Schwinger mechanism. Moreover, we can do quantitative comparisons specifically. And if we factor out from the ghost propagator, the part that we know is there, the tree level, what we are left with is a function that is called the ghost dressing function. And we can compute it within Schwinger-Dyson equations and the assumptions of the Schwinger mechanism. And we find that the result is on top of the lattice data. Okay, so these results really, they turn out to be within 1% of the lattice data. And they are the results that have been published in a recent paper that, in addition to me and Christina, also has Bianca, who's another student here there in the Institute of Physics. Now, this is a nice result. However, by itself, it does not prove much regarding the Schwinger mechanism, because it can be reproduced by some other models. So we were still left with the question, is there any smoking gun signal on the lattice that the Schwinger mechanism really takes place in QCD? That is there anything that is really distinctive, something that the Schwinger mechanism would explain and that other possible mechanism or lattice artifacts would not explain? And it turns out that yes, that this has been shown in a very recent paper. Okay, in fact, it has been published this year. And there we have shown that there is a certain quantity that the lattice can compute and that is sensitive to the Schwinger mechanism. The key to understand that is that the Schwinger mechanism, it generates gluon mass, but it preserves the gauge symmetry of the theory. And because it preserves the gauge symmetry of the theory, there are certain relations between Green's functions that are affected in a very profound way. Let us understand this before we show the results. So you will remember from either your quantum field theory courses or even just particle physics courses that the different Green's functions of quantum field theory, they are not completely independent. In addition to satisfying Schwinger-Dyson equations, which are dynamical, they also satisfy certain relations that are simply the results of symmetry. And in particular, we have the so-called Ward-Takahashi identities. So if we look, for example, at the case of scalar QED for simplicity, then the vertex that describes the interaction between the photon and the scalar, it satisfies a Ward-Takahashi identity, which is given by this equation. Namely, when the vertex is contracted with the momentum of the photon, the result is a difference of scalar propagators. So this is a completely general equation that follows from the gauge symmetry. Now, if you expand this equation around zero photon momentum, and you assume that this vertex does not have a pole at the origin, you will find a relation. Yeah, you can actually solve for the vertex at zero momentum, and you will obtain the well-known Ward identity, which is given by this equation. It says that the vertex at zero momentum is just a derivative of the scalar propagator. Now, unlike the Ward-Takahashi identity, which is completely general, the Ward identity is not. There is an assumption in deriving this equation from the Ward-Takahashi identity, and that assumption is that the vertex does not contain a pole longitudinally coupled to it. And that is precisely what the Schwinger mechanism changes in this whole story. So when the Schwinger mechanism is on, we can write the vertex in this form, a pole free plus a term containing the longitudinally coupled massless pole. And like I said, the Ward-Takahashi identity is completely general. It is not modified by the Schwinger mechanism. Okay, so when you construct the full vertex, that is pole free plus pole, you still have the same results, just the difference of scalar propagators. But now, if you do the Taylor expansion to obtain the limits of the vertex at the origin, the textbook Ward identity no longer holds. What you will find instead is that the pole free part of the vertex is equal to the derivative of the inverse propagator plus a term that comes from the pole of the vertex, right? The Bethe-Salpeter amplitudes. So just to recall, and it is this equation that will allow us to test whether the Schwinger mechanism happened in QCD, or more precisely, the QCD version of this equation. How so? Well, because these two ingredients that appear here, we can compute on the lattice. The pole-free part, like I said, it can be computed on the lattice. And the propagator can also be computed on the lattice, and then we can take derivatives from whatever we get, right? So then, if we compare these two quantities here, the derivative of the propagator to the vertex that the lattice computes, and we find them to be equal, that means there is no pole, that this amplitude has to be 0. But if they differ, that would mean that a pole in the vertex exists. And in the end, we can also compare the displacement of the Ward identity to whatever the Bethe-Salpeter equation predicts for this amplitude. So this exact same idea can be applied to QCD. Just it's more complicated because QCD is a non-abelian theory, right? So in addition to gluons interacting to themselves, we also have to consider that the gluons interact with ghosts, and that is really what complicates our analysis here. So instead of the Ward-Takahashi identity that we had for scalar QED, in the case of QCD, and in the particular case of the 3-gluon vertex that I am considering, what we have is what is called the Slanov-Taylor identity. The Slanov-Taylor identity, it relates the 3-gluon vertex to a difference of inverse gluon propagators, okay, the deltas here, but also to two other quantities that come from the interaction of the gluons with the ghosts. So in addition to the gluon propagator, we have the ghost stressing function that I had introduced before. And we have this quantity here that I'm denoting by the letter H, which is called the ghost gluon scattering kernel. And this encodes the interaction of the gluons and ghosts. But apart from the fact that it has more functions in it because of the non-abelian nature of the theory, the idea is the same. We can expand this equation around Q equals 0, and assuming that there is a pole in the vertex, we will get a Ward identity that is different from the textbook result, right? So if we carry out this procedure, if we write the vertex as a pole-free plus a longitudinally coupled pole, and we expand around Q equals 0, we will obtain an equation like this. In this equation, L, soft gluon here, is a particular projection of the 3-gluon vertex. And this can be computed on the lattice, okay, because it's a transverse projection, right? It is the quantity that the lattice can compute. Then we have on the right-hand side some terms that are usual, terms that appear in the textbook Ward identity, plus a term that comes from the pole, okay, and that displaces the Ward identity. Now, using this equation, we can try to test whether the Schwinger mechanism occurs in QCD or not. So the other quantities that appear here in the right-hand side of this equation are, well, the gluon propagator and its derivative. And I have already shown you the gluon propagator. This is, in fact, the quantity we're trying to explain, or more precisely, the saturation of the gluon propagator is what we're trying to explain. Then we have the Gauss stressing function that can also be computed on the lattice, right? So all of these three quantities, L, F, and delta, they can be computed on the lattice. And then there is only one ingredient that has not yet been computed on the lattice, and it is this function W here. This function W, it turns out to be a certain derivative of the Gauss gluon scattering kernel, and it can, in principle, be computed on the lattice, but it has not been done yet because it's actually very expensive to do so. So we resort to a Schwinger-Dyson calculation to compute this. Now, most of the ingredients that appear in this equation, in the Schwinger-Dyson equation for this function W, they are well known. We have, for example, again, the gluon Gauss propagators that I have already shown. We have the 3 gluon vertex, and in fact, only the pole-free parts that the lattice can compute contributes to this quantity. And we have the Gauss gluon vertex. All of this we have already very good understanding. There is just one quantity that we don't know, but there is evidence that this 4-point function here that we don't know is negligible. So we can just turn off this last diagram altogether and use this truncated Schwinger-Dyson equations to compute the W. And then finally, we have the last ingredients that we need to test whether the displacement of the QCD ward identity occurs or not. So when we combine everything together, we can test finally whether the Schwinger mechanism happens in QCD. To do so, we define first a null hypothesis. That is, we come here to this equation and we set C equals to 0. Okay, this is the hypothesis that the Schwinger mechanism does not occur. If the Schwinger mechanism does not occur, then the lattice 3 gluon vertex should be given by this combination. And when we compute this, what we obtain is the green curve up here. Whereas what the lattice finds are the points down here. So you see they are very far, right? So there is a very strong, very clear signal of a displacement in the lattice ward identity. And we can actually do better than just say that there is a displacement. We can compute from these results what should be then the Bethe salpeter amplitude by just taking the difference between these two curves, what it should be if there was no Schwinger mechanism and what it really is. And then we can compare whatever turns out from this difference to the Bethe salpeter prediction, and we find a very decent agreement. It's not perfect for sure, but it's a very qualitatively it's the same, and the quantitative differences are not too big either. Especially if you consider that, again, this Schwinger-Dyson equation that was used to compute the W there, and also this Bethe salpeter equation are truncated. They have some error built in. So when we combine all of this, we have not only shown that there is a displacement of the ward identity, which by itself alone would show that the Schwinger mechanism must be occurring in QCD, but in fact, we show that it is completely consistent within reasonable error to the Bethe salpeter prediction. So this is the main results, really. This is the money plot of this article. And with this, I can finally conclude. So QCD, as a theory of the strong interaction, it really hinges on dynamical mass generation taking place. Without it, you cannot explain the large hadron masses that we observe. Now, the quark mass generation is fairly well understood. We now know very well that the quark-gluon interaction is strong enough to generate a quark mass from that phenomenon of bifurcation of the Schwinger-Dyson equation. The gluon mass generation, on the other hand, is more subtle. It requires the formation of very special kinds of massless bound states that are not glue balls in the theory. to trigger what is called the Schwinger mechanism. That is what generates, in the end of the day, a gluon mass. To test whether this really occurs in QCD, we can combine lattice data for the propagators and vertices that QCD can compute with one function that we had to resort to Schwinger-Dyson equation to compute, namely this derivative of the ghost gluon scattering kernel W. And when we combine these results, we find that the lattice 3 gluon vertex is not consistent with a 0 amplitude for the beta salpeter amplitude of the Schwinger mechanism, right? We do need a non-zero amplitude for the massless poles, and moreover, the shape of this beta salpeter amplitude coincides perfectly, or well, as perfectly as it could be given the truncation errors of our analysis. So all of this together shows very strong evidence that the Schwinger mechanism is taking place in QCD. So with this, I finish. Thank you.
Thank you, Mauricio, for a very nice talk. So, have questions, comments? I have just, I have some things, but it's very small. Maybe it's more curiosity than anything. Can you go to your slide 9, please?
9?
Yes.
Yeah.
Good. I have just a question. As I understood, actually, these diagrams that you are showing are already truncations. Is it right or not?
Well, it's truncation because I have these dots here, right? So each line of this is complete, right? These are all of the diagrams that appear here. But you have an infinite number of these diagrams. The point here, maybe this is what might be giving you this impression, because you may think, where are, say, the 3-loop and 4-loop corrections?
Yes, that's my question.
Yeah, so the point here is that these quantities here, they are not, like I said, your usual textbook propagators and vertices. They are the full vertices. So this here is already the resummation, okay, the sum of all of the perturbative diagrams. Of course, we don't know what that sum is, okay? But that equation is precisely an equation that has that quantity as an unknown, right? So here you have every order of perturbation, right? So if you were to expand this in powers of the coupling, you would recover the perturbative expansion, right? So here you do have all loops.
Okay, yeah, that's my point, because the second diagram that you have is something like one loop, a topology of one loop, then a topology of 2 loop. Yeah. And the question was why there was no topology of 3 loop or something like that.
Yeah, so just imagine, for example, that you iterate this equation, right? Because you pick the right-hand side and put it back here. So you have one loop in the right-hand side, and you already have one loop here. So it will generate 2 loops and 3 loops, 4 loops, and so on and so forth.
Okay. Yeah. No, that's very interesting. Okay. Yeah. Okay. Because at some, just so seeing the diagrams is some way you only need the topologies up to 2 loop. So you have the topology, right? It is the topology of 1 loop or the topology of 2 loop, but you don't need the topology of 3 loop to reconstruct things of higher loops, of higher loop order, stuff like that.
You do. Again, it's hidden in these dots, right? It's hidden in these dots. By the time I go on and truncate this equation, you can show, for example, that it will generate all the perturbative corrections, for example, all up to 1 loop, but then at 2 loops, you will start missing some correction. You will have some 2 loop corrections, but not all of them. If you imagine that you were iterating this equation, the right-hand side back into itself. So they are there. They are hidden in these dots there.
Okay. So the dots, somehow they are going to show us different diagrams, because the first diagram is just let's think in perturbative quantum field theory, So you have just the propagator, that's only that. And then you have the vertex, and that's everything that you need for a normalization for a fifth form, right? But if you go with the dots, then you have different configurations, right? You have different legs or different configurations that you have to add. Okay.
Yeah.
Okay. Okay. And then
that's right. And that is what will give you all of the topologies if you want to think in terms of perturbations.
Okay. Oh, this makes sense. Good. And the other things, I mean, this is even more corrosive, but in your slide 11, you show us these two nice plots. So you have the one with the Schwinger Dyson and the one with the lattice. They agree very well. But somehow the Schwinger Dyson is a little bit smaller than the lattice result. And there is any explanation for that, or I mean, or not?
Yeah, so I said that quark mass generation is well understood. What I mean by that is that everybody agrees on the ballpark. Okay. But the exact result they do depend on the truncations, right? So these results that we obtained, it was computed within a certain approximation for this vertex, and like I showed before, right? This vertex will satisfy another equation that involves higher order vertices and so on and so forth. So there is a certain approximation here, right? So if you improve this approximation, maybe you will get better agreement to lies, right? So this now in the old days, when people put very simple things here, for example, for the just a tree-level vertex or some very simplified model, they wouldn't get anywhere close. In some models, they wouldn't even break chiral symmetry at all. They would not generate a mass at all. Okay.
Wow.
Now, in the last decade or so, a little bit more actually than the last 20 years or so, everybody has been converging, right? All of the most sophisticated, the state-of-the-art truncations, they have all been showing results that are in the same ballpark. The exact results, of course, it still does depend on the truncations.
Okay. And is there any way to, let's say, estimate the error that you have with the truncation, or is not possible? You have just to do the computation and then see.
This is really difficult. We actually had a paper out about estimating errors of truncations just this week. I mean,
nice.
In the archive, but this is really hard. We don't usually have analytic control. What we can do normally, the most systematic way is, imagine you were doing a series expansion, and then you compute the n+1 term of that series, and you take that, right? The n+1 would be an estimate of your error, right? If you can prove that the series converges, then you can say that the n+1 term is going to be the estimate of your error. You can, in principle, do something like this in Schwinger Dyson equations. You can say, for example, here we have computed this W only with these two diagrams. Now you could go on and add this diagram, and that would be an estimate of our error, whatever changes, right? And this diagram, it involves a 4-point function, which again would have to be truncated and so on. You could go be doing this forever. Now it becomes more and more complicated to add more diagrams, right? And very quickly. So, but there is evidence, from studies, from previous studies, that that there is a fast convergence path. So I quote here this effect that this diagram here, not in this particular context, not this particular derivative of the ghost-gluon vertex, but this diagram more generally, it has been shown to be only 2% of the total of these other two guys. All right. Again, there is some truncation into this, but it is an evidence that the thing is converging fast, and that these two diagrams alone should be a good estimate.
Oh, that's very nice. Oh, that's good. And maybe anybody has any questions?
Yeah, maybe I have like a small question on the cylinder model. And in that same page, that plot there is on the bottom right. There are different colors now. Why is that? Is that for the
you mean here?
Yeah, for the lattice results. Is it from different groups or?
Yeah, that's right. So what happens here is that lattice simulations, they, like I said, they have certain parameters that control their errors, right? Lattice spacing, for example, right? And lattice volume. And these are different lattice setups. Okay, in other words, each of color of points represents a simulation with a different set of parameters. So for example, you can see that the yellow ones, they only reach in the infrared. Why is that so? Because the lattice spacing is relatively large. Okay, so it goes inversely, right? So small lattice spacing means large momentum. So the yellow points here, they come from a lattice simulation that has a large lattice spacing. These gray ones here, on the other hand, they come from a lattice simulation that has very small lattice spacing. So now you do this, the people who do the lattice simulations, they use different lattice setups because it allows them to extrapolate to the continuum. So you combine results obtained from different spacings, and you do an extrapolation to try to refine your results and get what should be the continuum limits of the theory. Right? But they generally, you will plot the different setups all together. Okay, and that's why they have different colors.
All right, thanks. And yeah, just one thing in your slide 11, I guess. Where you
right,
show
slide 11.
Yeah, where you show that 350 MeV. Okay, that's for all quarks, right? For up and down, right? That's 350.
For up and down, that's right.
Down.
Yeah, for the heavier quarks, dynamical mass generation becomes less and less important as you climb up the ladder. Okay, so for the strange quarks, it's less important. The charm is even less important. So, right. So for the up and down, you essentially have no mass at the level of the Lagrangian. So the whole mass is coming from the dynamical mass generation. For, say, strange and charm quarks, what you will have is that if you were to plot it, you will start out something up here, and then it will go down a little bit, but then it will saturate to its current value, which is much larger here, right? So it's, you know, it's much less relevant. There is a little bit of an enhancement of the mass from this nonperturbative effect also in the strange quark, but much less important than what happens here for the up and down.
All right. So I missed the part for the gluon. It's something similar.
The difference for the gluon is that in the case of the quark, the mass, the dynamical mass, is associated to a very particular tensor structure, right? So when I show the propagator, I wrote it in this form. It has p slash in the mass. In the mass, it goes with a different Dirac structure than the rest of the equation, right? So, for example, imagine you take the trace of this equation, right? Or rather, the trace of the inverse of this equation. You see that if you take the trace, you isolate the mass, right? Because the gamma matrices will have zero trace, right? And if you multiply this by p slash and then take the trace, you isolate the z, right? In the gluon, it's more complicated because you have only one function, really. It's just that one function, delta, that has everything. So the delta, if you will, you can write it as q squared times a z, if you want, plus a mass, okay? You cannot separate them, so I cannot plot the mass in isolation as I do here. But we believe, okay, and we have done models in the past to try to understand the dynamical nature of this mass, because of course it's not a hard mass, it's not a constant mass. And we believe it should behave like this, right? It should be large in infrared and then go to zero in the ultraviolet, right? But it's not so simple as the quark to separate what is mass and what is not mass in that property, because they are not associated to different tensor structures.
Right, thank you.
Except at the origin, right? Except at the origin. Because at the origin, of course, the q squared term vanished, and then you're left only with the mass. But away from the origin, you don't have this separation.
So, any further questions, comments? I have just one more question. And you actually, maybe you said that, I don't know. But you have that function, the W function, that you actually don't have from lattice results, right? And then you had to do using the Schwinger. Actually, there is any, projection to do that with the lattice. Is it possible to do with the lattice?
Yeah, it is. It is possible, at least in principle, like I said. So it is associated, this W, it is actually associated to a transverse tensor structure of the ghost-gluon scattering kernel. So that alone is a very good start, because that's the only thing the lattice can compute. And in this paper here, this European Physics Journal C, we have actually given a formula for it, okay, in terms of things that lattice computes. Okay, lattice only computes essentially their correlation functions. Okay, so it's a sandwich of fields, okay, in the vacuum states. And we can express this quantity here, this W, as a derivative of an object like this, okay, that the lattice can compute, right? So it can be done in principle. But then imagine you do this on the lattice and you have results that are like these points going up and down, and you try to take a derivative of this. It's going to be nonsense, right? So you need to would need to have a huge precision on the lattice to be able to take anything out of it. So it's I don't see it being done in the near future unless somebody very clever on the lattice side figures out a more efficient way.
Okay, nice. Nice. So any further questions? If not, let's thank the speaker again and see you next week.